Good morning, everybody, and welcome to Unit 0, Back to Basics. We're going to start with right triangles. So, theoretically, you have learned your trigonometric ratios, and now we want to apply them to various right triangles. So, as a reminder, we can remember these using good old SO, CA, TOA. So tells us that the sine of an angle is equal to the opposite side over the hypotenuse. CA tells us that the cosine of an angle is equal to the adjacent side over the hypotenuse. And TOA tells us that the tangent of an angle is equal to the opposite side over the adjacent side. All right, so let's look at a couple of triangles today and see what we can learn using these trigonometric functions. So let's start with this triangle over yonder, this 5, 7x triangle. So first of all, we know two of the sides. We know it's a right triangle, but we don't know the hypotenuse. So if our goal is to find the hypotenuse, we can just use good old Pythagorean theorem. So as a reminder, that's a squared plus b squared is equal to c squared. So let's do that. So 5 squared plus 7 squared is equal to, let's bust out our handy dandy calculator. So we know that 5 squared is 25, 7 squared is 49, 25 plus 49 is 74. And the square root of 74 is 8.6. All right, so we know that our hypotenuse is about 8.6 long. Okay, so now that we know that, we can actually go figure out what all of these different angles are as well. So let's look at this angle first. Let's call this one theta. So now that we know all three of our sides, we can actually use any of our trigonometric ratios to figure out what theta is. However, I'm going to use tangent because I know the opposite side and I know the adjacent side. So the 5 is our opposite and the 7 is our adjacent. And I'm going to use those just because we calculated the hypotenuse, so there's a little bit of a rounding error that we could pick up in there. You could use the hypotenuse, but I don't feel like it. So using tangent, so tangent of theta is opposite over adjacent, so our opposite leg here is 5, and our adjacent leg is 7. Now, you'll notice that the thing that we are solving for is trapped inside of our tangent right now. So just like when we are solving math equations, and in order to get rid of something, we do the opposite operation, here we want to do the same thing. So our opposite operation of a tangent is an inverse tangent. So let's take the inverse tangent of both sides. So inverse tangent of a tangent cancels out and leaves us with what's inside. So it leaves us with our theta. So theta is equal to the inverse tangent of 5 over 7. Now when we're punching that into our handy dandy calculator, depending what mode you're in, so if you're in degrees mode, you're going to get degrees out. But if you're in radians mode, you're going to get radians out. So just be careful of what mode that you're in, so that you can get what you are looking for. So the inverse tangent in degrees mode tells us that angle is 35.5376779, so that rounds to 35.54 degrees. All right, so if this angle is 35.54 degrees, we can then figure out this angle up here. So let's call this angle phi. So now we could either go through the exact same process, or we could use our knowledge that the angles inside of a 90 or inside of a triangle have to add up to 180 degrees. So if one of our angles is 90, that means theta plus phi is equal to 90 degrees. So phi is going to be 90 minus theta. Well, theta we just found out was 35.54. So 90 minus 35.54 is 54.46 degrees. And ta-da! So using a combination of Pythagorean theorem, our trig ratios, and our knowledge of supplementary angles inside of a triangle, we can solve for pretty much everything we could possibly ever want inside of a right triangle. It's pretty handy. All right, so now let's check out this other one over here. Erase, 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 erase. All right, so in this case, we are given our hypotenuse and we are missing one of our sides. So let's actually skip Pythagorean theorem and start with finding our angles so we can see how that works. So I'm going to call this one theta this time. Now it doesn't actually matter which one you use. You could use both. It's just going to change which leg is opposite and which one's not. So 9, that's the hypotenuse of our triangle. So the 2, that's going to be our opposite leg. So we know the opposite and we know the hypotenuse. So let's use sine. So we know that the sine of theta is opposite, which is 2, over the hypotenuse, which is 9. We need to break theta out of its sine prison. So to get rid of a sine, we need to do the opposite. So let's take the inverse sine of both sides. So the inverse sine of sine theta is equal to the inverse sine of 2 over 9. Inverse sine of a sine cancels out, leaves us with just theta. So theta is equal to the inverse sine of 2 over 9. So if we punch that into our handy dandy calculator, the inverse sine of 2 over 9 is 12.84 degrees. Okay. So now that we know one of our angles, theta is 12.84 degrees, we can use that to figure out what this leg is here. So we know an angle, and we know the hypotenuse and the opposite, and we're looking for the adjacent leg. So since we're looking for the adjacent leg, we're going to want to use either cosine or tangent. So let's use cosine just because we haven't used it yet. So that we know the cosine of our angle is equal to the adjacent leg over the hypotenuse. So if we're going to use our 12.84 degrees, that tells us that the cosine of 12.84 degrees is equal to our adjacent leg, let's call y, over our hypotenuse, which is 9. So to get our adjacent leg, we want to multiply both sides by 9, so that the y is by itself. So y is 9 times the cosine of 12.84 degrees. All right, so 9 times the cosine of 12.84 degrees gives us about 8.77 as that leg, which makes sense because it is shorter than our hypotenuse, which it better be if it's a triangle. And we can actually go back and check that with Pythagorean theorem if you feel so inclined. All right, so let's try a couple more. So now in this case, we're only given one of the sides and we're given one of the angles, and we're looking for the hypotenuse. So given the angle that we know the opposite side, and we're looking for the hypotenuse. So opposite hypotenuse, that tells us that we want to use the sine. So sine theta is opposite over hypotenuse. All right, so let's plug in our values. So the sine of 50 degrees is equal to the opposite, so 6 over our hypotenuse. Let's actually just call that x, so we don't have to write hip all the time. All right, so now we're solving for x. So we can cross multiply insofar as my x goes over there, and then my sine 50 comes down here. So I skipped a few steps here, but I'll leave it as an exercise to see if you get the same thing. All right, so x is equal to 6 over sine 50. So let's punch that into our handy dandy calculator. So 6 divided by the sine of 50 degrees gives us a hypotenuse of about 7.83. All right, and that is a reasonable answer as it is longer than one of our sides. All right, so let's check out this one. So here we're given both of our angles and we're asked to find our hypotenuse. So we can actually use either of these. So let's set it up. So if we use the 60, the 4 is our adjacent leg and we're looking for hypotenuse. So that means we would want to use cosine. Cosine is equal to adjacent over hypotenuse. If we were to use the 30, however, that's the opposite leg. So that means we would want to use the sine of 30 is 4 over the hypotenuse. So one thing that I want you to notice is that the cosine of 60 is the same as the sine of 30. So that's a fun little factoid about complementary angles inside of a right triangle, is that the cosine of one is equal to the sine of the other. So one way that we can actually write that is that the cosine, let's call this one theta, the cosine of theta is equal to the sine of 90 minus theta. So remember that 90 minus 60 gives us 30. So those two add up to 90, right? So this is one of the identities that you're going to see a lot when we're talking about trig functions if you're in pre-calc or calculus, is that the cosine and sine are just a 90-degree phase shift away from each other. And that's going to make a little bit more sense when you dig into trig a little bit more. All right, so let's go back to solving these. So cos 60 is equal to 4 over c. So if we solve that for our hypotenuse, c is equal to 4 over the cosine of 60, or c is equal to 4 over the sine of 30. So 4 over cos 60 gives us 8. And 4 over sine 30 gives us 8. So we did get the same answer, which is great. And ta-da! So that is our super fast intro into right triangles.